So, welcome you all in my next lecture. So, in my last lecture I introduced the notions of directional derivatives, and I said that okay, existence of directional derivative in all directions will give you the existence of partial derivatives. However, whether the converse is true, that means can you give some examples where you have the existence of partial derivatives, but existence of directional derivative in some directions do not exist. So, those kind of examples I said that I will provide in my next lecture. So, I will start with that, and then you will see that once I have done with the directional derivative, the concept of directional derivative, then I will talk about the notions of total derivative, and that is one of the kind of important object in this direction. So, and then I will try to compare that is there any relations between partial derivative, directional derivative and total derivative. And maybe in the later, if time permits, then I will talk about the what is called tangent plane and normal line of a surface. So, that is the plan. Okay. So, as I said in my last lecture, so I should give one example where I can ensure you, okay, yes, look, this is the example where you have the partial derivative exists at some point, however, the directional derivative does not exist. So, I was trying in my last lecture, in fact, this is the example where I missed one t in the calculation, you have to be very careful. For example, this is the example where it says that partial derivatives exist, but directional derivative along other direction do not exist. Look, so this is the function, this is kind of very nice function you might have seen in my earlier lecture. Now, I ensure you that okay, partial derivative of f at 0, 0 and partial derivative with respect to x variable with respect to y variable at 0, 0 exists, that you check it, it is very straightforward from the calculations. Now, I would like to ensure you that okay, what can I say about the direction derivatives. So, yes, earlier in my last lecture I was trying to do is do the same calculations, then I was one t is missing actually. Okay. Look, so what I have to do, limit t approaches to 0. If I want to calculate the directional derivative of f in the direction say a b, where a b is non-zero at the point 0, 0. So, what is the definitions? Definition is f of 0, 0, this point, plus t times a comma b minus f of 0, 0 divided by t. So, that is that t I was kind of missing in my last lecture. So, look, this is limit t approaches to 0, okay, 1 by t as it is. So, what is this? This is f of t a comma t b minus f 0, 0, f 0, 0 is given. So, that means this is the one I have to calculate. So, what is this? This is limit t approaches to 0, 1 by t, and what is f of t a t b? So, the f of t a t b, that means since a b are non-zero, so this is given. So, this should be t a t b divided by t square a square plus t square b square. And what is this? This is limit t approaches to 0. So, that numerator t square and denominator t square will get cancelled. So, this should be a b divided by a square plus b square, but there is a 1 by t, and that t will make you a problem because it is constant, you can take outside, right, but this limit does not exist. So, that means whatever the directions I am taking a b where a is non-zero, b non-zero, directional derivative does not exist. So, this is the example and shows you that existence of partial derivative will not imply existence of directional derivatives. In other words, this is the moral from the earlier examples in my previous slides. What I am trying to say is that, so let f is a function from a subset of Rn to R, S is an open set in Rn, x naught is a point in S, take a vector u in Rn with norm is 1, that means unit modulus. Then look, so partial derivative of f at the point x naught in the directions u exist for all. So, that means if the directional derivative of f at x naught in all direction exist will not implies the continuity of f at x naught. So, the example I have seen. So, that means that example says that directional derivative at the point in all directions exists, however, my function is not continuous, that example. Not only that, if my function is continuous, that also does not implies that directional derivative of f at x naught in any directions will exist. That is also true. That means no one implies other. That means existence of directional derivative at some point in any direction will not imply the continuity of f at that point. Continuity of f at that point will not imply the existence of directional derivative in any directions. So, it is not possible. This is I already discussed. If the directional derivative of f at the point x naught in any direction exists, in particular it will exist in the coordinate axis direction. So, therefore, the partial derivative exists. However, existence of partial derivatives will not imply the existence of directional derivatives or in any direction. So, that is just last example says. So, therefore, so these are the concepts, they are mutually independent. So, no one implies other. So, that means if I want to have the kind of if and only if or equivalent criteria, then I need some more extra assumption or that maybe in later slides you will see if I put some more extra assumption, then in that case some of them implies are kind of other one actually. But in general it is actually independent, that means existence of directional derivative or existence of partial derivative will not implies the continuity and vice versa. Okay. So, this is again properties of directional derivatives like properties of partial derivatives, you know. So, like sum, scalar multiplications, dot product, chain rule, which will be exactly similar whatever I have discussed in case of partial derivatives. You just replace the coordinate axis directions ei by any directions, similar kind of results will follow. Okay. So, this is one part. Second part is that again if, as I said, okay, this is the kind of notation means statement. If duf at x naught exists for all unit vectors, then I will say that f is said to have directional derivative in all directions. So, that means if the directional derivative of f at the point x naught in any directions will exist. So, that is why I say that directional derivative exists in all directions. So, that is a kind of statement or notations you can say. Okay. So, till now whatever I have discussed is the existence of or notions of partial derivatives, notions of directional derivatives. Is there any connections between existence of partial derivatives and continuity, existence of directional derivatives and continuity? Those are the things I have discussed. But the main point, if you remember, that whether I am talking about directional derivative or partial derivatives, what I am doing is that given my functions from Rn to R, if I want to talk about a directional derivative in some directions, so once I keeping my directions fixed, that means even if I am in Rn to R functions, but still I am kind of restricting myself on a one dimensional line, that means given a directions, think about the line passing through the origin, and then I am keeping my functions from R to R and doing the derivative that we are familiar with. And that is how it gives the notions of partial derivatives if I perform the directions in coordinate axis directions, and directional derivative means you do not have to look at the coordinate axis directions, you look at any direction. So, that is how it is. So, that means there are no more changes, just I am again restricting myself from R to R and doing the things. Now, the question, or in other words I should say that I am looking at the kind of changes of the kind of, if I want to talk about the directional derivative at some point x naught, that means I am actually looking at the variation of my point x naught in one direction, that means in one line actually. But if I am in R2 or R3 or Rn, because there are for given point there is a ball, but I want to, or I would like to see the changes of my point x naught if I disturb in any direction. That means I am not interested to see the changes of my point in one direction. I would like to see the changes of my point x naught in any directions. And that brings you the concept of what is called total derivative. That is very strong. So, then you will see that this, once I have this existence or notions of total derivatives, then automatically it will implies the existence of directional derivatives and implies the existence of partial derivatives. So, that is the kind of major part I should say. But before that, okay, so I say that okay, what are the kind of learning outcome in now on? It says that if I have a functions f is a subset of Rn to R, where S is an open set, so then I will give the kind of notion of total derivative. As I said, I want to see the changes of my point x naught with some small perturbations in a neighborhood of x naught, not in one direction. Okay. What is the notion of total derivative? And then I will say that if the total derivative exists, then I will say that just f is just differentiable. No partial derivative, no directional derivative, just I will say that f is differentiable. If I say that f is differentiable, that means I am talking about the total derivative. Okay. If f is differentiable at x naught, then of course, as in the kind of real valued functions with real value, you know that existence of derivative implies the continuity. I also demand this setting as well. The notions I will give, it should implies the continuity, and it is indeed the case, it will implies. Then I will talk about the gradient vector once I have the notions of total derivative, grad of f at axis naught and some of its properties. Then I will give some necessary conditions on for differentiability, okay, like as I said that just existence of partial derivative and directional derivatives will not allow you to talk about the differentiability or existence of total derivative. There are some certain conditions are there. So, that is called sufficient condition. Necessary conditions, if I have the total derivative, then what can I say? As I said, existence of total derivative implies the existence of directional derivative, and once I have the existence of directional derivative in all directions, that means partial derivative exists. Of course, converse parts you may ask, so whether existence of partial derivative and directional derivative will, when can I say about the existence of total derivative? Those are the things I will talk about in my coming lectures. Okay. Not only that, once I have the total derivative, then I can write the expression, because total derivative implies the existence of directional derivative. Not only that, I can write the directional derivative of my functions f at x naught in the directions u in terms of the total derivative. You calculate the total derivative, take the inner product with the vector u, it will give you the directional derivative of f at x naught in the direction u. And then, as I said, sufficient conditions for differentiability, that means existence of partial derivative of directional derivative when it will implies the existence of total derivative, and along with chain rule. Okay. Before I give the definitions of total derivative, this is just one remark. I already discussed why that existence of total derivative is important, or why I would like to introduce the notions of total derivative, why partial derivative and directional derivative is not enough to talk about the differentiability of f. So, this is the main drawback. The main drawback of the directional derivative of a function f at a point x naught with respect to a unit vector u is that it only gives a picture of the behavior. So, that is I have written, it only gives a picture of the behavior of f near x naught on one dimensional set. So, as I said, so this is only one dimensional set, that means x naught plus tu, only in that one dimensional set I am looking at the changes of my x naught, only in that one dimensional set, not in a neighborhood of x naught. It is only one direction, so I am looking at the changes. So, in order to obtain more complete information about f in a neighborhood of x net, that means if I would like to see the changes of x net in a neighborhood of f, I would like to see the changes in all possible directions, not in that one dimensional set x naught plus tu. We shall introduce the notions of derivative of f, that means that I am talking about the total derivative, and which is a linear map. So, that means now is the linear map or linear transformation come into the pictures. Before that, I will define what do I mean by linear map or linear transformations. So, if I have n dimensional Euclidean space Rn and Rm, so that means let T be a map from Rn to Rm, we say that T is linear map or linear transformation if it satisfies these properties. That means T acting on x plus by, it should be exactly equal to a times Tx plus b times Ty for all vectors xy in Rn and scalars ab in Rn. So, if a map satisfies these properties, then I will say that T is a linear transformation. There is another information. So, suppose you have Rn Rm. So, since Rn has orthonormal basis consisting of n vectors, Rm has orthonormal basis consisting of m vectors. So, if I have e1, e2, en, e1, e2, em be standard basis in Rn, Rm respectively, then there exists an m cross n matrix A such that the linear transformation T can be written as Tx is exactly equal to Ex. So, what I am trying to say is that, so if I have a linear transformation T from Rn to Rm, then there exists a matrix m cross n such that T of x is exactly equal to the action of the matrix A on the vector x. So, if that means if I have a linear transformation, I will have a matrix, and also converse. If I have a matrix, I can have a linear transformation from, suppose if I have a m cross n matrix, then I will have a linear transformation from Rn to Rm. So, if I have a matrix, then I will have a linear transformation. If I have a linear transformation, then there exists a matrix such that the action of T on x is nothing but A times x. This is one correspondence is there. So, once I have, okay, I will say that the matrix A is called the matrix representation of T with respect to the standard basis. So, this kind of things you might have seen in the linear algebra courses, like there is a one-on relations between the linear transformations and the matrix. If I have a matrix, then it will induce a linear transformation. If I have a linear transformation, then I will have a matrix A such that the action of T is same as the action of A on the same vector x. So, this kind of things, the kind of connections between linear transformations and matrices you might have seen in the linear algebra courses. So, I need only those two pieces of information to talk about the total derivative of a functions f from Rn to R. Okay. So, look, so that is how I will start. So, first you think about your definitions of differentiability from R to R that you are familiar with. Okay, that is why I will recall. So, recall the differentiability of f from AB subset of R to R. So, this is the conventional, that is kind of definitions you are familiar with. What is that? Suppose f is differentiable at the point x naught AB, if there exists a alpha such that this limit exists, and I will say that this is nothing but derivative. So, what I am saying is that, so if I want to talk about the derivative of f from open interval a b subset of R to R, then you know the definitions. If I want to talk about the differentiability of f at x naught, what you do? You calculate the limit h approaches to 0 of the quotient f of x naught plus h minus f of x naught divided by h, and if the limit exists, and that limit I am talking about the derivative of f at the point x naught. Okay. So, and of course, you note that alpha is unique as far as the x naught is concerned. That means, if the derivative exists at the point, it is unique, because if limit exists, limit is unique. So, that is how it follows. That is one of the way. Now, I would like to see the above one in this form. How I can see? What we have to do, look. So, you know, this is the kind of definitions you are familiar with. What I am doing is that, so this is same as, or if and only if I should say, limit h approaches to 0, f of x naught plus h minus f of x naught divided by h minus alpha, this is 0, right. So, I am just taking alpha in the left hand side or right hand side, so this is 0. Then what I am doing is that this is same as limit h approaches to 0, f of x naught plus h minus f of x naught minus alpha h divided by h. This is 0, same, right. So, what I am doing is that h get cancelled, only alpha will be there. So, I am just writing the same object like this and like this. And what is the existence of this? This is nothing but limit h approaches to 0 of something is 0. That means actually the mod is 0, because I am talking about the existence of limit with respect to some metric or some distance. In R, what is the distance? Absolute. So, that means this is nothing but, so this is same as, you can say that this is limit h approaches to 0 modulus of f of x naught plus h minus f of x naught minus alpha h divided by h, that is goes to 0, and that is exactly equal to this, right. So, that means you take the mod in the numerator, in the denominator. So, that means in the earlier I will have this, the looking at the derivative in this way, but now I would like to see in a different way. So, I am saying that f is differentiable at x naught if there exists a alpha such that limit h approaches to 0 modulus of f of x naught plus h minus f of x naught minus alpha h mod divided by mod h is exactly equal to 0. That I can see, right. Earlier definitions you can convert it to that part. So, that in that way I would like to see my definitions. Again here alpha is unique as far as my point x naught is concerned. So, once I see my definitions in this way, now what I am saying is that, look, this is another way, or this is I should say, that is I have written. First one is the conventional, and that is actually given in the definitions in many books. Second one was the clever way. You can just, instead of just looking at only the limit of the quotients, you bring the limit in one of the sides, do the kind of some algebra, and think about this quotient of this, and this is 0. Smartest way I should say is that f is differentiable at x naught if there exists a linear transformation T from R to R such that this is 0. Then you say that how linear transformation come into the picture? Look, what is alpha? Alpha is in R, okay. Now, if I have a alpha, then each alpha in real number will induce a linear transformation, say let it be T alpha from R to R. And what is the action? T alpha x is nothing but alpha x. So, that means each real number R will induce a linear transformation. Similarly, if I have a linear transformation from R to R, then you will have a real number such that your linear transformation T is exactly equal to T suffix alpha. So, each alpha R will induce a linear transformation T alpha, whose action you can easily say T alpha x is equal to alpha x, where x is in R. Conversely, if I have a linear transformation T from R to R, there exists a point alpha in R such that T exactly equal to T suffix alpha. So, that means there is a 1-1 correspondence between the linear transformation from R to R and the point alpha. So, that exactly I am doing. Earlier I have a point alpha, now I just replacing that alpha by T alpha, because I know the actions of the linear transformation T alpha on H is nothing but alpha H. So, now the smartest way to look at the definition is that I am saying again from the real variable case, from functions from R to R, f is differentiable at the point x naught in open interval a b if there exists a linear transformation T such that this is 0, f of x naught plus h minus f of x naught minus h mod divided by mod h goes to 0, and note that this linear map T is unique as far as the point x naught is concerned, okay, because alpha is unique. So, therefore, given T alpha, this is also unique, that the linear transformation is unique. So, now if someone will ask what is the definitions of derivative at some point for functions from open interval a b subset of R to R, I will say that okay, now onwards I am looking at the definition like this. F is differentiable means if there exists a linear transformation or linear map from R to R such that the limit of f of x naught plus h minus f of x naught minus the linear transformation acting on h modulus divided by mod h goes to 0. Once I have this observation from the real to real, then I can easily extend this definition in the context of Rn to R, and that will give you the notions of total derivative. This is the definition, total derivative. It says that, okay, start with the functions f from some subset open set S subset of Rn to R. Okay, let x naught belongs to S, and I would like to talk about the existence of total derivative at the point x naught. I am saying that the function f is differentiable. Look, just I am talking about differentiable, no partial, no directional, nothing. So, the function f is differentiable at x naught if there exists a linear transformation from Rn to R such that this is true. What is this? This is limit h approaches to 0. So, that means if I am in Rn, h approaches to 0 means what? Norm of h goes to 0. So, h approaches to the vector approaches to 0 means actually this is if and only, that is the definitions, norm of the vector goes to 0. So, if there exists a linear transformation T from Rn to R such the limit h approaches to 0, f of x naught plus h minus f of x naught minus t acting on h divided by norm h, this should go to 0. Now, you can say that, okay sir, the range of f is in R, so norm should be replaced by mod. Okay, that is fine, you can replace it by mod. But my point is that it is actually work in the definitions for functions f subset of Rn to Rm, that is also. Because in that case what will happen? Because in the domain we have Rn, so that means that norm I am talking about Rn norm, okay. And in the range you will have a R, that means you will have a mod, and if you have a Rm, that should be Rm norm. So, that means same definition will be there in the, when I will talk about the total derivative or existence of differentiability of my function from Rn to Rm at the point x naught, same definition will be there. Instead of here mod, the corresponding norm, that means wherever the range will be there in the space Rm, that norm I am talking about, that distance I am talking about. Okay. So, therefore, even I can say that if I have a function f from S subset of Rn to Rm, suppose my function f is differentiable, I'll say that a function f is differentiable at the point x naught if there exists a linear transformation from Rn to Rm such that limit h approaches to 0, norm f of x naught plus h minus f of x naught minus the linear transformation acting on h. So, everything will be in the range space, that means Rm, that means the norm I am talking about in the numerator Rm norm. In the denominator I am talking about h in the space Rn, so Rn norm. If that norm quotient is go to 0, then I will say that my function is differentiable and the derivative is nothing but that linear transformation. Here actually Rn to R, though I am writing its norm, but you can write it as a mod itself, because norm is nothing but mod in R. Okay. So, what I am saying is that this is the conclusion. So, suppose you have a function S from Rn to Rn where S is an open set, let x naught belongs to S, the function f is differentiable at the point x naught if there exists a linear map T from Rn to R such that this should go to 0. That means this quotient should go to 0. Quotient means in the numerator you have norm of f of x naught plus h minus f of x naught minus t, linear transformation acting on h divided by norm h. The linear map T is called the derivative of f at x naught, and this is the notations. So, I will say that df at x naught, f prime at x naught, or f prime at x naught df x naught is nothing but the linear transformation. So, till now from the real, for the functions from R to R, I know the derivative is nothing but a real number, but that real number I can think about in the case of functions from R to R as a linear transformations. So, now that concepts I am bringing here in the case of Rn to R or Rn to Rm. I am saying that if I have a functions from Rn to Rm or Rn to R, if I want to talk about, I want to say the notions of differentiability of f at some point x naught, that means if the derivative exists or total derivative, if the derivative exists, I will say that yes, my function is differentiable and the derivative of f at x naught is nothing but the linear transformations. Okay. Okay, I have written a note, the quantity derivative at x naught is called the total derivative of f at x naught to distinguish it from the partial derivative and direction derivatives. So, if I just say that derivative, you might have confused that, okay, do you mean that it is partial direction? No. So, if I want to say that if function is differentiable, so that means it is actually that I am talking about the total derivative. So, that is I am just giving the name the total derivative. So, once I talk about the total derivative, that means I am talking about the existence of differentiability in this sense. Okay. Let us see some examples, it will be more clear. Okay. It is a very simple example I am considering, say f of x y is equal to x square plus y square. So, then it is a functions from R to R. Okay. So, the questions examine the differentiability of f at some point, say x naught is equal to 1 comma 2. So, that means what you have to do. So, you have to somehow, as I said, that means if I want to talk about the existence of total derivative or derivative at the point 1, 1, 2, that means there is a linear transformation or linear map associate. Okay. That means first you have to guess, okay, so look, this is my linear transformation. So that probably, the first you have to guess something, that probably the total derivative of my functions at that point. And then you have to show that, see, to show that yes, it is indeed the case, that means you have to check that limit of h goes to 0, that the norm quotient should exactly equal to 0. So that's you have to do. So first consider the linear transformation R to R. Okay. So I am just guessing first. Okay, let's see, this is the linear transformation t of xy 2x plus 4y. Suppose, okay, this is linear transformation, you can easily check, it's a map from R to 2R, it is linear. Okay. But how to guess t, that, okay, that's the questions, like you can say that, sir, how can I guess t? Well, in my next lecture I will say that, okay, you can actually guess, there is a way to guess what linear transformation might work to check the total derivative or differentiability of f at that point. That I maybe in next lecture I will talk about that. But for the time being, you assume that, okay, I am having some one linear transformation. So this is the linear transformation. So that means what you have to do, you have to just calculate that the limit of this quotient of norm, this should go to 0, that's it. What you do, take a vector h is equal to h comma k, just compute this object, that means f of x naught plus h minus f of x naught minus t acting on h, t is given, you already guessed something, so that means numerator you know, you just calculate the norm, divided the norm of h, and you just see whether that limit exists or not. Okay, let's see. H approaches to 0 means what? Of course, as I said, I am in R2, so that means h approaches to 0 means actually I am talking about the norm of h. Norm of h means hk vector goes to 0, that means I should say that h square plus k square, that this is goes to 0, that's what I am talking about. That means the Euclidean distance from origin to hk, that is goes to 0. Okay. So let's see the calculations. Okay. So this is the one I would like to see the limit of this object. Okay. So norm of f of x naught plus h minus f of x naught, so everything is there, x naught is given, x naught is 1 comma t, so therefore I have to calculate the norm of 1 comma 2 plus h is given h comma k, so that means this is, I have to see f of 1 plus h comma 2 plus k minus f of 1 comma 2 minus t acting on hk, so it is a linear transformation acting on hk divided by norm of hk. Again this is limit hk goes to 0 0. So now if the definition of function is given, f of x comma y is equal to x square plus y square. So what will happen? So this is 1 plus h square plus 2 plus k whole square, that is the definition. Again 1 square plus 2 square, and this is the linear transformation I already said, guessing part. Okay, 2h plus 4k. Do some algebra and the calculation, you will end up with this kind of object. So in the numerator you will have h square plus k square plus norm. Norm means nothing but modulus. So this is positive, so that means in the numerator you will have h square plus k square, denominator you have square root of h square plus k square. So what we will have? Only square root of h square plus k square. And this is hk goes to 0 means, that means the distance between origin and hk goes to 0, so therefore the limit is 0, right. So therefore what I am saying is that, yes, look, so I want to calculate the total derivative of my functions at the point x naught. First, this is the guess, this linear transformation might work, and then once I fix the linear transformation, I am just calculating this object limit, and I am saying that this is 0. So therefore I am saying that f is differentiable at 2 comma 2 and derivative is t. Then you might ask another question, sir, okay, so this I'm fine with this linear transformation. Does there exist another linear transformation so that the same calculation proceed? Answer is no. If the derivative exists, derivative is unique. That part I will talk about that. So if the total derivative of f of my function at some point exists, it is unique. So therefore once we have the proper guess, that is exactly the total derivative. You don't have to worry about there are other linear transformations will not work. No, absolutely not. Only the total derivative exists means only if you guess one linear transformation such that the limit of the quotient is 0, norm of the quotients, then of course this is the unique linear transformation, and this is nothing but the total derivative of my functions at that point. Okay, so this is actually earlier I have just same functions. I am talking about the kind of total derivative at the point 1 comma 2. Now this is the same example, but I just change this 1 to 2 arbitrary point x naught y naught, so that what sort of guess I can have for the linear transformation. Okay, so again, so same thing. So first you have to consider a linear map from R2 to R, and then somehow you have to calculate the limit of the quotient. That's it. So here again I am saying, okay, so take this is the linear transformation. That means t of x y, it should be x naught y naught is fixed. What I am doing is that 2 x naught times x plus 2 y naught times y. So again this is a linear transformation, you can easily check. Just you have to ensure that, okay, if the limit of this quotient is 0, then I will say that this is the linear that linear transform is nothing but the total derivative of my function at that point. Okay, let us see, do the calculations. That means I have to perform to calculate this limit. Again, just you have x naught, you have hk, everything is there, definition of function is there, use the calculation. So that is, this is nothing but this is same as this, that means f of x naught plus h comma y naught plus k minus f of x naught y naught minus t h k. T, you know what is the action, so you have x naught plus h whole square plus y naught plus k whole square, this is minus x naught square plus y naught square, this is the actions you know from the linear transformation. Again, if you perform some algebra, you will end up with same object. So that means this mod is nothing but just h square plus k square, because it's positive. Norm, actually norm means what? I am actually in the R2 to R function, so that means it's give the value r. This is a positive number, so mod is, you don't have to put the mod. So that means h square plus k square. And denominator is a square root of h square plus k square, so that means this is. But hk goes to 0, so what will be the limit? This is limit is 0. So therefore, now I have a linear transformation, limit of the quotients of this is 0, so therefore the function is differentiable and derivative is nothing but t. So that's how one can calculate. Okay, so that's as I said. So like if the derivative exists, whether it is unique or not, answer is yes. Derivative at the point x naught is t and t is unique. Okay, I am writing addition as well. That's what is it. That is the case. Okay, suppose, so how to prove that it is unique? So take, you have two linear transformation for which both the quotient is 0. That means take one linear map T1 from Rn to R, another map T2 from Rn to R, such that this is true. That means limit h approaches to 0, this quotient norm, so that means this quotient of the norm, that means f of x naught plus h minus f of x naught minus T1 of h divided by norm h, it is 0. And suppose and the same time limit h approaches to 0, norm of f of x naught plus h minus f of x naught minus T2 of h, this norm divided by norm h is 0. Suppose I have this informations I have, then I have to show that T1 is equal to T2. Then I will say that if the derivative exists, it is unique. So I have to show that T1 is equal to T2. So you take the linear transformation T1 minus T2, which is again a linear transformation L, because sum of two linear transformation again a linear transformation. I have to show that L is 0. What I am doing is that, okay, so start with any positive epsilon. So since this limit is 0 for both T1 and T2 is given, right? So that means just use the epsilon delta definition. So that means given epsilon, I will have a positive delta such that if norm h lies between strictly positive and less than delta, this quantity will be less than epsilon, that you know. That's the definitions of the limit goes to 0. So that means given epsilon, I will have a delta such that norm of f of x naught plus h minus f of x naught minus tjh, norm h is less than epsilon, and that should work for j is equal to 1 comma 2. When in fact I should say that if j is equal to 1, you will have one given epsilon, you have one delta 1, and if I have j is equal to 2, you have another delta 2. You just take delta is minimum of delta 1 and delta 2, and that delta will work for both T1 and T2. That's exactly I have written. So given epsilon, you will have a delta such that if norm of h lies between 0 to delta, so this quotient is always less than epsilon, and it is true for j is equal to 1 and 2. Once I have that one, then what I am doing is that consider h is a vector in Rn, suppose 0 less than norm of h is than delta, then what I am doing is that norm of LH divided by norm of h, that is the object I would like to compute. So this is same as L is given T1 minus T2, it is linear, so therefore T1h minus T2h divided by norm h. Then what I am doing is that this is dominated by this object. So how do I get that one? So this is easy in a sense that you just do add and subtract, right? So what I am doing is that I am just adding this term, because I have T1h minus T2h. What you do, you add and then subtract. So then you combine f of x naught plus h minus f of x naught, then T1h, okay, and then f of x naught plus h minus f minus T2h. So if you do that, then it will be true. Okay, so you just add this term and subtract. So that means what I am trying to say is that T1h minus T2h, which is same as f of x naught plus h minus f of x naught minus T2h. So let it be take, and then with a minus sign f of x naught plus h minus f of x naught minus T1 of h. So add and subtract, nothing else I am doing, and then use the triangle inequality of the norm. So you will end up with this object. But what is given? Because since 0 less than norm of h less than delta, so each of them is less than epsilon. So therefore this is less or equal to 2 epsilon. So that information I have. So then next what I am doing is that, and this is true for all norm of h strictly greater than 0 less than delta. Then what I am doing is that take any non-zero H star, non-zero I am just, since I am taking the non-zero vector I am putting the star marks here. So then what I am doing is that fix H star is a non-zero vector, then I am hitting with T H star. So that means I am in that one dimensional subspace T H star. Okay. So therefore I am considering this, instead of I am just replacing H by T H star, I am replacing capital H by T H star. So what will happen? Norm of L T H star divided by norm of T H star. Now L is linear, so T will come outside, and in the denominator norm of T H star, T will come outside. Okay. So that means T T will get cancelled, in fact what will get cancelled, what I will have, this is the object. Okay. Now look, so I already proved that if given epsilon, I will have a delta such that this is, if I norm of H is less than delta, then this object is less than epsilon. So now look, what I am doing is that I am starting with a non-zero vector, I am hitting it by T, and then I am talking about T goes to 0. Now if T goes to 0, then norm of T H star, this vector also goes to 0. If this is goes to 0, so that means what will happen? This implies that, that means norm of LH by norm of H, this is also goes to 0. So that's what, and now since I am hitting with T, T will get outside. So that means this goes to 0 as T approaches to 0, but this is remain constant. So that means I am talking about the vector or the point norm of L H star divided norm H star, this is 0. Now this is a non-zero vector, so therefore L H star is 0, and for every H star, and therefore L is 0. L is 0 means what? I have to show that the linear transformation is 0. That means I have to show that the action of L in any vector is 0. So to show that, first you will have this estimate, that means whatever vector H I can take in Rn, if the norm of H is strictly less than delta, then norm of LH divided by norm of H, which is less than epsilon. So that's the first, you have to conclude that. Now if norm of H is goes to 0, that means norm of LH by norm of H, this is also goes to 0. That's the property you have to use. How to use it? Okay, so choose a vector, non-zero vector H star, hit it by T, and let T goes to 0. Now if T goes to 0, then norm of T H star will be goes to 0. That means norm of this L H T H star divided by norm of T H star, that is also goes to 0. But norm of L T H star divided by norm of T H star, which is a simple single vector, which is norm of L H star divided by norm H star. That means this is 0. That means H star norm is non-zero. That means L H star norm is 0, and so therefore H star vector is 0. And this is true for any arbitrary vector, non-zero vector. So therefore L is 0. So what I proved is that, so if the total derivative exists, the linear transformation I am getting, it is unique. That means if the total derivative exists, it is unique. So that means if I want to say that, okay, calculate the total derivative, if you somehow guess one linear transformation, and if you somehow show that, okay, look, this is the quotient of, so I have this linear transformation guessing part, then I am calculating the limit, and this goes to 0. So therefore this is nothing but the total derivative of f at that point. That's it. Okay, so this is another part. Okay, so as I said, okay, so in real variable case also you will have the observation that if my function is differentiable, then it is continuous. So in that case, what will happen? If I have the existence of, say, total derivative of my functions at some point, then what can I say about the continuity of my functions f at that point? Answer is yes. If f is differentiable, that means if the total derivative of f at the point exists, then it is actually continuous functions. So that's I have written as a theorem. Okay, so let f be a functions from some set A subset of Rn to R, where S is an open set in Rn. Let x naught be a point in S. Now if f is differentiable at x naught, then f is continuous at x naught, and that actually one I should guess that, okay, differentiability should implies the continuity. So now since f is differentiable, that means there exists a linear transformation such that limit h goes to 0, that norm quotient should goes to 0, the norm of f of x naught plus h minus f of x naught minus the linear transformation acting on h, this norm divided by norm h is equal to 0. That's, so suppose f is differentiable means that this is the linear transformation, this is goes to 0, then what I am doing is that consider this vector norm of f of x naught plus h minus f of x naught. What is this? This is, so I want to talk about the continuities. That means I want to show that, okay, the limit h goes to 0, f of x naught plus h is exactly equal to f of x naught. If this is the case, then I am done. So that is why I would like to estimate this object, norm of f of x naught plus h minus f of x naught. What I am doing is that you just add and subtract one th, okay, then use the triangle inequality. So this is dominated by this plus this, that is by triangle inequality. Okay. Now this is lesser equal to f of x naught plus h minus f of x naught minus h as it is. Now, this is lesser equal to m times norm h. Why? Because I have a linear transformation t from what? Rn to r, that means I have a linear transformation from t from Rn to r, right. So, if I have a linear transformation t from Rn to r, you can prove that t acting on h, this mod or norm, whatever it is, this is lesser equal to, you will have a fixed constant m times norm of h. So, that is a kind of, I am not saying in details there. So, this is kind of, if I have a linear transformation, this is actually bounded. This is kind of bounded linear transformations, because I mean Rn to r, it is finite dimensional Euclidean space. So, there always exists a m such that this is true for all h. Okay, that you can get it. For the time being, we assume that yes, this is the case. So, once I have this one, I mean this is dominated by this object, then what I am doing is that suppose epsilon is 0 given, there exists a delta such that this is true, because in your hypothesis what is given, that my function f is differentiable, that means total derivative exists. That means this is given, limit h approaches to 0, norm of f of x naught plus h minus f of x naught minus th divided by norm h, that is equal to 0 given. So, therefore, given epsilon, I have a delta such that if norm of h is less than delta, then it should imply this object norm of f of x naught plus h minus f of x naught minus th, which is should be less than epsilon, that means this should be epsilon times norm h, right, because of the definition of limit. So, given epsilon, if this is less than delta, so this numerator norm is dominated lesser equal to epsilon times norm h. Combine these two things, if I have this one, then this estimate will give you this one. So, this is dominated by this difference by epsilon times norm h plus m times norm h whenever norm h is less than delta. This is actually existence of the total derivative of it. And this is true for every h with this one. So, now you just take limit h approaches to 0, h approaches to 0, if I take that one. So, this is, that means in the right hand side, look, if h approaches to 0, that means epsilon is fixed, m is fixed. So, therefore, this is goes to 0, this is goes to 0. So, therefore, the right hand side goes to 0 and therefore, the left hand side goes to 0. And left hand side goes to 0 means what? That means if limit h approaches to 0, f of x naught plus h is exactly equal to f at the point x naught, value of f, and this is nothing but the continuity. So, that should be the case, right. So, that means it is quite natural. So, like in the real variable case, you know that differentiability implies continuity. In that case also, I think that once I have the notions of total derivative, it should imply the continuity, and answer is yes. Yes, once I have the existence of total derivative at that point, that means my function is continuous. Okay. So, I think I should stop here. Okay. So, next lecture I will talk about the like gradient of f, and then like another few properties of like gradient or like partial derivatives, and some related properties of the total derivatives. So, or maybe chain rule will be there, that I promised you, and there should be connections. So, once I have the existence of total derivative, then of course, directional derivative exists, but there is a formula that if I have the total derivative, then you can have the formula for the directional derivatives, and then we will have a chain rule. So, those are the concepts I will see in my next lecture. Thank you.